Welcome back to ECE 320A. We're in Unit 8, still in Chapter 13, working through homework number 8, and exam number 3 is upcoming at the end of Unit 8. What we want to do in this video is to actually derive the impulse response of the low-pass filter. Here, the low-pass filter that I'm using is a first-order passive RC circuit, and that's the one that I'm referring to as the low-pass filter. There is no only low-pass filter, but there are many different low-pass filters, and we'll see how to create higher-order low-pass filters in subsequent material. But today, what we want to do is just focus on finding an impulse response associated with a particular low-pass filter, and that's this first-order passive RC circuit. So we'll compute the transfer function of our low-pass filter, and then, knowing the connection between the impulse function as an input and the output response, we know that we can find the impulse response of our system by simply inverse Laplace transforming the transfer function that we've just computed, which is the inverse Laplace transform of the low-pass filters. Maybe I should say inverse Laplace transform the low-pass filters transfer function. Let's now compute the impulse response of this low-pass filter. It's an RC circuit. We have our input X, we have our output Y. We might as well utilize what we've now learned in terms of quickly analyzing this without having to find the time domain governing differential equations. Now we can immediately go into the S domain equivalent circuit of this system. The resistor comes over unchanged. The capacitor now is a generalized resistor, or it now has an impedance of 1 over SC, and all of our signals are now in the frequency domain. We have the Laplace transform of our input, that's capital X of S, and we have the Laplace transform of our output, which is capital Y of S. And then we have a way of looking at this. If we want to, we could call this particular resistance and impedance Z sub 1, and this particular energy storage device has a particular impedance Z sub 2, but in general, anything could be in those boxes for Z sub 1 and Z sub 2. And we can now look at finding the transfer function, capital H of S, between the input X and the output Y in terms of these general impedances Z sub 1 and Z sub 2. And then at the very end, we can back substitute what Z sub 1 and Z sub 2 actually are. But for the transfer function, we now know that that's going to be the ratio of the Laplace transform of the output waveform to the Laplace transform of the input waveform. And what we want to do now is find capital H of S, and that's doable if we can find an equation for Y of S, the output voltage across that capacitor, in terms of the source or the excitation signal, capital X of S. And if you remember or think through some of your circuit analysis by abstracting this circuit into a Z1 and a Z2, this is a series circuit, you can now see, hopefully, that the output voltage Y is related to X by a simple voltage divider equation. So that Y of S, in terms of X of S, becomes as follows. We can say that Y of S is now simply going to be the output impedance, Z sub 2, over the sum of the impedances, which is Z1 plus Z sub 2. That now scales the original signal X of S. This is now a voltage divider that we've used to quickly find an abstract connection between the input X and the output Y. But now that we have this in terms of Z2 and Z1, we know what Z2 is in terms of more particular expressions. That's 1 over SC, and Z sub 1 is simply R in this particular first order low pass filter. Or now we have 1 over SC all over R plus 1 over SC. That may look a little bit ornery because of this ratio of ratios, but we can clean it up by getting a common denominator of SC in both the numerator and the denominator. Those will cancel, or we could think of multiplying both the numerator and denominator in this black boxed expression by 1, where 1 is now SC over SC. However you want to think about that, but now we can see that we have 1 over SRC plus 1. That now is what is scaling our input waveform, capital X of S, and this particular boxed quantity is the transfer function that we were looking for. So our transfer function now, and this particular transfer function is written in a special form, and that's this time constant form, where the time constant tau is RC, the RC product. In order to find what we want, we probably want to go ahead and think about this transfer function in a different representation, but we can now say that H of S is either 1 over S RC plus 1, or we could factor out the RC. We could make the denominator polynomial monic by normalizing the coefficient of the highest power of S in the denominator to be 1. And now we would have then that RC we could put up into the numerator, and we have S plus 1 over RC. This is now in pole zero form. It's equivalent to what this time constant form was. We haven't done anything to change the transfer function, capital H of S. We've just rewritten it a little bit differently, but this pole zero form now allows us to think in terms of exactly where our poles are, and that should help us when we want to inverse Laplace transform capital H of S. And that's really the next question. What happens in our system when the input waveform, little x of t in the time domain, is in fact the impulse function? And we just derived that in a previous video. Now, when x of t is equal to the impulse function, then in the frequency domain, we have capital Y of S is equal to capital H of S, because the Laplace transform of our waveform, little x of t, is 1. So now we know that Y of t is equal to H of t. And this then is called the impulse response of our system. And we can find that now. Now that we have capital H of S written in pole zero form, we can now find Y of t is now equal to H of t, which is just the inverse Laplace transform of H of S, which in pole zero form has the following structure. If we factor out the numerator from that inverse Laplace transform expression, now we should be able to very easily identify this expression. This now should look like just a 1 over S plus A that is in all of your Laplace transform tables. Now we can inverse Laplace transform that expression, and we have 1 over RC times the inverse Laplace transform of 1 over S plus A, but that's now just e to the minus a t, and A is 1 over RC. So this is e to the minus t over RC, and that's true for t greater than or equal to 0. Or, if you wanted to think about this, what is y of t or h of t in this particular first order low pass filter at time t equals 0? E to the 0 is 1, so we have an amplitude of 1 over RC, and it now exponentially decays. Here is now our 1 over RC times e to the minus t over RC. When t is equal to RC, or when we're one time constant into this response, we're now down by a factor of e to the minus 1, or 37% of where we started. And within, so this is now 1t, or one time constant tau, if my sketch is somewhat accurate, which is RC. And if we went all the way out to 5 tau, this would be our 1% settling time. And that's when we effectively say, okay, our response is finished after 5 time constants, or a 1% settling time. That's e to the minus 5, which is less than 0.01 in actual value. Now, think about what this looks like. This is the impulse response of a low-pass filter. And we haven't yet determined what the parameters of that low-pass filter are other than R and C. And now you can maybe start to see what happens as we adjust this time constant RC in our low-pass filter. For example, if we make this time constant RC smaller, if RC now goes down, then what happens to 1 over RC? That's not a very challenging question. It's now going to go opposite to what RC did. So now 1 over RC is going high, or going very big, and as we make RC small, 1 over RC gets big. Or another way of thinking of this, if RC gets small, then the pass band of the low pass filter actually gets broader or wider. So if RC goes down, then 1 over RC goes up, and the pass band of the low pass filter, I don't know if you want to say increases or broadens, but it goes up in concert with 1 over RC. Look at what 1 over RC. If 1 over RC gets bigger, then this pole moves further into the left half plane, and that now makes our low pass filter have a wider band width. And because of that, now the low pass filter passes more frequencies, and as 1 over RC gets very, very big and RC gets small, do you see that that tau gets very close to 0? 1 over RC gets really, really big. What's going to happen to this impulse response? As 1 over RC, or as RC gets small, 1 over RC gets big, then h of t is actually going to approach delta of t. And that now says that if our low-pass filter has a very, very wide bandwidth, we're going to be passing all sorts of frequencies, then our output waveform is going to look very much like our input waveform. There won't be much filtering of the input to get to the output. So when h of t looks more and more like an impulse, then When h of t, our impulse response, looks like the ideal impulse, then y of s, which is h of s, x of s, looks more like 1 times x of s, or now that we're passing all of the frequencies, then the output's going to look just like our input. That's the more our impulse response looks like the ideal impulse function. So y of t looks like x of t when h of t looks like delta of t. And remember, h of t is our impulse response of our system. And we could look through all of this analysis or think through this particular thought process by simply starting with a very basic low-pass filter and allowing those parameters to be adjusted. So the low-pass filter actually provides us with a very strong intuitive feel for this concept of the impulse response and how a system will respond based on the shape or the waveform of its particular impulse response.